Fourier series, what I say, then there are other topics which linear algebra, including some part of abstract algebra. This is basically preliminary in order to understand linear algebra. And then basically another two things, Laplace transformation and Fourier. Okay, so these topics, this is up to your online classes. Okay, and these three, basically these topics will be covered offline. Okay, so for your information, I like to tell you, so you will be getting new academic building for the classes, which are all AC rooms. Okay, so at this temperature, this will be some beneficiary for you, as well as me also. So I like to come to the introduction of Fourier series. Why we should read Fourier series? This is the question from where I like to start. And as I told earlier, the book I follow, that is Introduction to Laplace Transform and Fourier Series by Phil Dyke. So this book, I am having the soft copy. If you need, you can take from me, or maybe you can buy this book. Okay. So many phenomena in the applications of natural and engineering sciences are periodic in nature. That already all of we know. Examples are vibrations of strings, springs, and other objects, rotating parts in machines, the movement of the planet around the sun, the tides of the sea, the movement of a pendulum in a clock, the voltage and currents in electrical networks, electromagnetic signals emitted by transmitters in satellite, light signals transmitted through glass fibers, like that. These are all, you can say that periodic in nature. So all these systems operate in complicated way. The phenomena that can be observed often behave in an erratic way. So our idea is to have like standard periodic functions like sine function and cosine functions. Okay, so all of we know the graphs of these functions, and these are very nice function in a sense that sine function and cosine function, these functions are uniformly. It is having a power series representation which converges uniformly to sine and cosine functions, and these are very standard periodic function whose period is of 2 pi, right? What is the period of this periodic function sine x and let me first define, suppose
2 by
Pi sin x, there will be pi.
2.
okay, so see, f is
So
said to
2 pi.
be, yes, 2 pi is the correct answer. So what is the definition? If f of t plus capital T is equal to f of t for all t belongs to the domain.
So then
Uh,
capital T will be the periodic time for that function.
so t is any positive number. So
Yes, sir.
then you can say that if there exists some capital T such that it happens, means it happens to be repetition, happens to be repeated after a certain stage, then we can say that it is a periodic function, and the period of the function is basically the smallest such positive number t, right? So
Yes,
period
yes.
is what? See, for example, sine of x is a periodic function, and I can write sine x is equal to sine of x plus twice pi, right? So even it is equal to sine of x plus 4 pi. But can you say that this 4 pi is the period of the function? No, because this is not the least positive number. So
Yes,
the
sir.
lowest positive t
That will
for
be
which,
2 pi.
yes, that will be 2 pi. So period of the function is 2 pi. Similarly, you can find the period of this sine pi x uh, and several other functions. You can find the period. So the functions which are not periodic, like ft equal to t, you can say that it is not a periodic function. So in that situation, we can think of it is having an infinite period, right? So infinite period means we assume that the function repeats its value after infinite interval. Okay, so in those cases we can have Fourier basically integral representation. So basically the Fourier, mathematician Fourier, initially in order to examine the heat vibration of string problem, there he assumed that mm, that every function can be represented as the sine and cosine series. It is having representation, but later on, basically it is very difficult to give the proof. But later on, it has been proved by some other mathematician, Dirichlet, that and this is not the case. Uh, in case of periodic function, particularly, which are piecewise smooth, then you can expect that it is having a Fourier series expression or representation, where we can say that the series expansion also converges to the function itself for all x, right? So this is the basically brief development, and the advantage is huge. One of the biggest advantage is that there are so many well-known series, and one very connected series is like that summation 1 by n square. So this is a very famous series, all of we know. This is convergent, that also we know. It is very easy to give the proof that the series is convergent summation 1 by n square. Even summation 1 by n to the power p is convergent whenever p is greater than 1. All of we know. And
Yes, sir.
okay, but where it converges, that is again a big question. So we being Indian, we are proud to know that this particular series summation 1 by n square is convergent, and it converges to pi square by 6. It is equal to actually pi square by 6. So it has been given the proof by Ramanujan, right? So Ramanujan gave the proof in one fine morning. He shouted
So
that
how,
I
sir?
what?
So how he proved?
Okay, how he proved that I do not know. But just I like to give some brief around this. But now after the class, we are in a position to give the proof very easily. Okay, so that much I can tell you. So the thing is that in very early morning, he shouted that I got the proof. It goes to pi square by 6. And when he told other colleagues, uh, then they are surprised. Then how you know that it goes to pi square by 6? He said that God says that. Okay, so this is because of his intuition. He said that it goes to pi square by 6. You know, pi is a number which is transcendental, not a rational number. It is an irrational number. Pi square by 6 is also transcendental. The series 1 by n square goes to pi square by 6. This assumption, or intuitively, it is very, very difficult. And after once he claimed that thing, it took around 1 month time to give the proof that it is actually pi square by 6. So it has been proved possibly by means of the infinite series expansion, Fourier series expansion. Okay, but I am not very much sure. But after today's lecture also, we are in a position to give the proof. Okay, so there are several other series where it converges. That thing also we can find by means of Fourier series. And also in the beginning, I told that the phenomena where it can be applied, and what is the advantage once some arbitrary periodic function is there. If we can express in terms of sine and cosine series, then we are in a very healthy situation, right?
Yes, sir.
Okay, so now
Yes, sir.
let us define what is basically Fourier series, and then we will go ahead. Suppose if is a function, initially we define the function whose domain of definition basically we assume to be minus pi to pi, and the function is real valued function. So our starting assumption will be fx is equal to, sorry, small fx, small f, which is minus pi to pi to r. and this is a periodic function of period twice pi, the length of the interval domain of definition. And we initially also assume that it is a piecewise continuous function, right? Then it has the Fourier series. F has a Fourier series Fs as follows. So please you write Fs Fourier series. What is that? Half a naught plus summation n cos nx plus bn sin nx. How a naught can be found by means of Fourier integral. So this is nothing but your 1 by pi integration minus pi to pi fx dx, and n is equal to 1 by pi minus pi to pi fx sin nx dx. Not sin n
Cos, no, sir. Cos.
cos nx, yes,
Yes, sir.
cos nx. And what is bn? 1 by pi minus pi
Minus
to
pi to
pi
pi. F sin
fx
nx.
sin nx dx, right? So for all here for all n greater equal to 1, this is your these things basically n a naught n bn, these are known as the Fourier coefficient.
Sir, all of this will be provided in the PPT or we have to copy?
No need to copy because this is already recorded, and I am having the lecture note that will be shared after the class.
Okay,
Right?
sir. Thank you, sir.
Okay, so no need to copy it. You can see the screen, that's fine, and try to understand it. Okay, so
Sir,
yes.
sir, can you repeat the piecewise continuous? I cannot exactly remember what it is.
Okay. Suppose whatever the function, in general case, I like to tell you, right? Then for the particular case, you can define at your own. If suppose A to B.
Sir, can you show the previous slide?
Previous slide.
Sir, Fourier coefficients. Sir, Fourier coefficients.
Yes.
Okay, sir.
Okay. Now come to the piecewise continuous. Continuous, all of you know, continuous on an interval means it is continuous at each and every point of the domain of definition. But piecewise continuous, from the terminology, if we try to understand that, it may be discontinuous at finitely many points, only at the finitely many points inside the domain of definition. Say for example, suppose this is your A comma B. So there may be certain finitely many points, x1, x2, up to xn, where the function is not continuous. Then we can just write or um, we can expand the domain in this way. Suppose a comma x1, this is open. Another is x1, x2, this is again open. So I can omit the points like xn open, b closed. So these are the subintervals where function becomes continuous. Understand? So if a function is not continuous throughout the domain of definition, at the best, we can expect that the function is discontinuous at the finitely many points. So we can express the domain of definition in finitely many subintervals, just deleting the points where the function becomes discontinuous. Then we can say that the function is continuous rest of the things. That means like here function becomes continuous. So those type of function we can expect that it is we can have the name, it is piecewise continuous. That means piece means here it is continuous, here it is continuous, like that. So I think it is clear.
Yes, sir,
Yes,
it is clear.
Okay. Now,
Sir, how,
so
excuse me, sir.
Sir,
How the
what if the
formula
function
of
is
Fourier
not
coefficient
discontinuous?
come?
what? I
Sir,
cannot understand.
sir, how the formula of Fourier coefficient come?
Okay, so this formula basically, okay, it involves so many things, particularly sine function and cosine functions if we take. So those functions are orthonormal, those forms an orthonormal sequence in a function space like CAB. CAB is a function space. If you define the orthonormality or the inner product there by means of the standard inner product in CAB. So at this moment, it is better not to discuss because it will take more than one class to discuss how these things are coming. Okay, because these
Sir, what
development
is the limit of the summation?
limit of the
Summation in Fourier series?
n greater equal to 1. That means n equal to 1 to infinity.
Yes.
Infinite Fourier series, series expansion in terms of sine function and cosine function. See, these are very standard periodic functions, and this function f is an arbitrary periodic function which is piecewise continuous. Then we can expect that it can be represented as a series of sine and cosine functions. Okay. Okay, so let us first solve some exercise in this respect. If I take a very simple function like fx equal to 0 whenever minus pi less or equal to x less than 0, and it is 1 whenever 0 less or equal to x less or equal to pi. Suppose this is your function and f of x plus twice pi, it is extended periodically with the period x in the whole domain of definitions of real number. Or maybe I am little bit flexible here. I can make it minus pi to pi. So there is no issue. So I make the function to be periodic. So we have to find the Fourier coefficients and the Fourier series itself. So you know the function is basically it is a periodic function. It has been extended and the period of the function is twice pi. Okay. So we can find a naught is equal to what? 1 by pi minus pi to pi fx dx. So what is this? Who can tell?
1, sir, 1.
1 by pi minus pi to 0. So it will be 0 dx plus 1 by pi 0 to pi. It will
dx.
be
Dx.
just dx,
Dx.
right? So what is this? 1. Very good. Next, what is your an? An is 1 by pi, similarly minus pi to this part 0 to pi. This part is basically 0, you know, this part, so no need to write it. So it is 1 into cos nx dx. So what is the value?
Sine.
N.
So 1 by n.
So what is this?
0.
1 by
Value of
pi
n 0.
0, sir.
So 0, that will be.
nx.
0.
So this will be 0. Very good. This is for all n greater equal to 1. Now what is your bn? 1 by pi. Here again minus pi
0
to
to
0.
pi.
This is 1 into sine
Sine nx dx.
nx dx. So what is this?
1 minus
2 by
minus
pi
1
n.
to the power n by n.
2 by pi n.
See, this is minus
1 minus minus 1 to the
2
power
by
n
pi
divided
n.
by n.
this will be cosine, right? Nx.
Yes, sir.
So 0 to pi. Okay. Now we like to do this calculation. So this means minus 1 by n pi. This is cos n pi means minus 1 to the power n
Yes,
and
minus 1.
minus 1. Okay. So that means what? 1 by n pi.
So that depends on the n.
Okay. For all n greater or equal to 1. So what will be the Fourier series? Then Fourier series of fx. This is half of a naught. Half of a naught means 1 plus summation n greater or equal to 1 n cos nx plus bn sin nx. Right?
Yes, sir.
So this is okay. Should I write it a naught? So half into 1 plus summation n greater or equal to 1. This is an is equal to 0. So bn equal to 1 by n pi 1 minus minus 1 to the power n. This is sin nx. Okay, so this is basically your Fourier series. Now the question is regarding the convergence of Fourier series.
So what is the significance of a Fourier series?
Significance, see, uh, suppose you are given a function which is just periodic function. So this could be very much arbitrary. And if you can express, okay, I can come back to the problem in case of in general and then come to the Fourier series. Suppose f is a function which is particularly continuous. Now, you know, polynomial functions are also continuous. Pnx. Any polynomial function is continuous, uniformly continuous, very nicely behaved function, right? But arbitrary continuous function, suppose you are having. So in that situation, what suppose the function is continuous, a to b fx dx. If the function is continuous, then it is integrable. So, but it is not guaranteed that whether you can find the integration explicitly. I can give one example like that, 0 to 1 sin x squared dx. Can you find the integral? No, because the function is continuous, okay. That means the function is integrable. That is also okay. But since we do not know the primitive of the function, that means we do not know any capital Fx whose derivative is sin x squared. That is why we cannot find the value of the integration by means of fundamental theorem of integral calculus, right? So it is always beneficiary if we can express any continuous function in terms of some polynomial function, Pnx. Means what? Suppose epsilon greater than 0, mod of fx minus Pnx, this is less than epsilon. So this is a polynomial function. So that means what? Suppose you are having a very small amount of error, that is your epsilon. Then the continuous function and a polynomial function is difference is less than that particular small number. That means we can approximate the function in terms of the polynomial function. So this is a views theorem. This is by Lagrange's or Weierstrass approximation theorem. You can we can tell. So this is the base of your numerical integration part. So using numerical integration, we can integrate this thing and we can find the approximate value of this function. Okay, so this is one part. Another thing, this is very model thing. I expect that the function is a periodic function and function is not at all continuous. It may be piecewise continuous. Whether we can express that function in terms of standard periodic function like sine and cosine, and in addition to that, if the series, this series particularly Fourier series is convergent, uniformly converges to the function fx for all x belongs to the domain of definition, then we are having huge advantage because function is arbitrary, which is periodic and piecewise continuous. If we can express in terms of sine and cosine function, then certainly we are having the beneficiary thing. So these functions are very much standard. It's graph and everything we know. So now I think you understand it. The motivation behind knowing the Fourier series. And also another motivation, so many series we can find where it converges, and there are several other. Okay, now the thing is like see Fourier convergence theorem. If your function is periodic function with the period twice pi and the functions are piecewise continuous, then we can express that, we can say that the uh, where the function is continuous, it converges to fx, and where the function is not continuous, then it converges to what? This thing. That means average value. Half of f of x plus means what? Right hand limit. And half, another thing is that f of x minus, that is the left hand limit. So in general, we can tell that it converges to there. Then we can tell if suppose f is continuous, f of x plus f of x minus. If f is continuous, then we know that both left hand limit and right hand limit are same, and that is going to be equal to f of a, right? So that means what? Ultimately, it is half of twice f of a. That means it is f of a. So if that is for particularly x equal to a point, and if it is arbitrary, then it is going to be f of x. That means where the function is continuous, there it converges to f of x, the function itself. Where the function is not continuous, there we have to find the limit, left hand limit and right hand limit, and we have to take the average. That means f of x plus right hand limit plus f of x minus means left hand limit divided by 2. That means we are considering the average value where it will converge. So one important thing that the function is periodic, f is periodic. This is the necessary condition. Another sufficient part is that it is piecewise continuous, PC. And also we can express that, also we can say that if it is piecewise smooth, PS, piecewise smooth means what? That means we can say that f dash x, left and right f dash x, left and right derivatives exist at each of the points. Smooth means it is basically continuously differentiable, and we expect that it is piecewise smooth means at finitely many points where the function is not continuous, therefore the function is not differentiable there. So we can say that except those points, functions its left derivative and right derivative exist. Okay, so that is what your piecewise smooth. If a function is piecewise smooth, then we can say that the Fourier series of a will converges to the point f of x plus f of x minus divided by 2. Whatever I already wrote it.
But I couldn't get piecewise smooth function. What is it?
Sir,
The
so by
function
the
is
time
continuous
period
at
has to be
right
2 pi.
1 minute. I just like to give the answer first. piecewise smooth. Suppose these are the points where the function is not continuous. That is what your piecewise continuous. So that part already you understand. So if I omit this point, okay, if I omit this point, so here the function is smooth. Here the function is smooth. Smooth means continuously differentiable. Here the function is smooth. Here the function is smooth. This is basically piecewise smooth.
Okay, sir.
Okay.
Yes, sir.
Okay. Now I like to tell you one remark, that is, from the above theorem, the fact f is piecewise continuous, only if we take the assumption that f is piecewise continuous, then it will
Sir.
give the guarantee. Wait. It will give the guarantee that Fourier coefficient can be found. Okay, that means we can find the an and bn. Now the another part, the condition that f dash is also piecewise continuous. So smooth means continuously differentiable function, as I told you. If this is also piecewise continuous, is a sufficient condition to guarantee that the series thusly found will be convergent everywhere on the real line. Understand? So it has two parts. We have to understand this thing is very, we have to be very cautious here, that the series is convergent everywhere on the real line, provided if this is piecewise smooth. Okay. If it is only piecewise continuous, then we can say that we can find your this an and bn. Okay. What is your an and bn? These things. These are the Fourier coefficient we can find. That means this integral will exist and we can find the Fourier coefficient. That means Fourier series can be found. In addition, if it is piecewise smooth, then we can say that the series will be convergent. So series will be convergent. That is very much essential. Why? Because otherwise we cannot find that where actually it goes to. That means summation 1 by n square or any other series where it goes actually converges, that we cannot give the guarantee. Okay. From this fundamental theorem of Fourier convergence theorem, or fundamental theorem related to Fourier series, so that theorem is an important tool to say uh, where actually function will converge. Okay. Now another question is asked by some student. Okay, now I move forward to another thing, that is, suppose f is a piecewise continuous function. Initially, I assume that the function is defined on minus pi to pi. F is defined on minus pi to pi to r. Okay, but it may be defined here arbitrary interval minus L to L. There is no issue. And the period of the function is basically twice L, length of the domain of definition, period of the function. Then also we can express the Fourier series, that is the same thing here, n cos nx. Here what is? X is replaced by n pi x. That means x is replaced by pi x by L. Okay, so if this is a function which is a homeomorphism, that means what actually we do, minus pi to pi, this interval, and minus L to L, this interval, these are ultimately homeomorphic by using this transformation. So what we have to recall it, just x we have to replace by pi x by L, and everything else is fine. So what will be here? A0 is 1 by L minus L to L. Earlier it was 1 by pi minus pi to pi. Here it is 1 by L minus L to L fx dx. And you know, cos nx earlier, it will be cos n pi x by L. Here also sin n pi x by L. This is the only change you can find from here. So ultimately what we have to do, we have to just replace x by pi x by L. That's all. So this is if I like to find the triangular wave function defined by fx equal to mod x, where the domain of definition is -1 to 1. It is not -pi to pi. And the function is extended periodically. That means what is the length of the domain of definition? -1 to 1. That means length is 2. That means what? F of x plus 2 is equal to fx for all x belongs to -1 to 1. So ultimately what happens? The function is periodic
What is a
on the
triangular
interval.
wave function?
Yes, triangular wave function. This is.
The meaning of triangular wave function?
It looks like triangular, and it is since it is a repetition, so it is like wave. Wave, you know, it is a repeating nature. Okay, so if you draw the curve, then you understand it. So what is happening here? Okay, I'm coming here. It will be smoother. As f is from -1 to r, like x goes to mod x. Is not it? This is your function. And another condition is that f of x plus 2 is equal to fx for all x. Belongs to the domain of definition, right? So if I try to draw the curve, so what happens? This is, say, for example, -1. This is your 1. So 0 to 1, it will be what? This thing. It will be x. Whenever -1 to 0, it will be minus of x. What is that? What is the curve of minus of x? At x equal to -1, it will be 1. Understand? So it will be again, it will goes like this way. So this is like a wave. And this is like a triangle. That is why it is triangular wave. Okay.
So what is homomorphic? So you just now said.
Homeomorphic means yes, bicontinuous bijection. If two intervals or two spaces are homeomorphic, then their topological properties are equivalent, means are same, exactly same. Homeomorphic in general definition is that suppose A and B, these are two space, or in general it is X and Y. These two spaces are said to be homeomorphic if there exists a function f from x to y, which is continuous, bicontinuous bijection. Continuous, and f inverse is also continuous. So I write it is bicontinuous and bijection. Why bijection is necessary? In order to have the existence of f inverse. So f is also continuous, and its inverse mapping from y to x, that is also continuous. Then topological properties will be same, because topological properties are determined by its open sets, and open sets are nothing but continuous functions can be defined in terms of the open sets. A function is said to be continuous if for every open set here we can have, suppose O is open set here, we can have f inverse O is again open in X, then we can say that the function is continuous. So it is all about the characteristics, depends on the open sets. So if it is a bicontinuous bijection, then we can say these two spaces are homeomorphic, right? So minus pi and pi, this can be embedded in minus L to L and the vice versa. Okay. Now, in this case, all of you can, I think, say, for example, particularly A naught, you can find
How we will find A naught?
1 by, what is L?
L.
1 by pi.
1 by
One, sir,
L?
one.
1.
You have to one.
This is
-1
-1
to
to 1
mod x.
fx dx. Means
Yes, sir.
mod x
Mod
dx.
x
dx.
cos.
So this thing,
dx.
no, this is a naught. Then
Yes, sir.
the
Yes,
n,
sir. Yes,
It
sir.
is okay, sir. Okay, sir. 1 minus 1 to
minus
0
1 to
minus
1,
x dx
Mod x
minus
cos
this is cos
n pi
n
x.
cos n
n pi
pi
x.
N pi
x
x.
by l, n pi x
1.
by l,
1, sir.
1
Yes, sir.
dx. So this thing integration all of you can
So how
find.
this is coming?
By the rule.
Okay, you know, again, how many times I will tell? Minus pi to pi, this is the standard domain of definition. Now
Yes, sir.
here
Minus
the
L to L.
minus L to L. What is
Yes, sir.
the x goes to where? Pi x by L. So this mapping I used. So instead of x, you have to put pi x by L, and the accordingly the domain of definitions you have to change by minus pi to pi to minus L to L. So that is why I am doing minus 1 to 1 L, minus L to L. And x এর জায়গায়, in place of x, I write pi x by L, right? So Bn is minus 1 to 1, mod x is your fx,
Sin
Sin n.
n pi
pi
x by 1
1 dx.
dx.
So these things all of you can find, and you can find the Fourier series.
Yes, sir.
Okay.
Yes, sir.
Now come to some other points. Half range Fourier series and half range sine and cosine series. The idea is like that. Suppose your function fx is defined in the half interval 0 to L, and it is required to express fx as a sine series. It is in advance, it is said that you have to express your fx, the given function, in terms of sine series. This is important. And what is the period? Period is twice L, but your range is domain of definition. Initially, it was 0 to L, half. That is why half range, half
Yes, sir.
terminology is coming. Okay, now we extend the definition of fx in the other half. Other half is what? Minus L to 0, right?
Yes, sir.
Yes, sir.
This is 0, this is your L. So other half is minus L to 0. Here the function is defined, and we have to find the half range sine series, suppose. That means in this case, what we have to extend the function oddly. Odd function, do you know? Odd function and even function we
Yes,
have to.
sir.
Yes, sir.
Yes, sir. F of
Yes.
minus x
F
equal
of
to
minus
fx.
x to minus of fx.
Yes.
Yes, sir.
F of x is equal to minus of minus.
No, sir.
F of
Yes,
minus
sir.
x, sir. Minus of f.
F
Yes,
of
sir. Yes, sir.
minus
Right,
x.
sir. Right,
Right,
sir.
sir.
This is
Yes,
right.
sir, right.
This
Right.
is for
Yes.
odd
Yes, sir.
function. And
Yes,
even
sir.
function,
Yes.
what is the definition of even
Sir,
function?
they
F of
will
x
be
is
equal.
equal to
They will
minus
be
x.
equal.
Of minus x.
Okay.
So they will be equal.
Yes,
Yes,
very
sir.
good. So, sine function is even function or odd function?
Odd
Odd
function,
function.
sir.
Odd function, sir.
Even
Odd
Odd.
function.
Sine function
Odd
is
function.
Odd function.
odd function. One
Odd
one
function.
standard example. There are many examples. And cosine function
Sir,
is
symmetric about
Even
even.
function.
yes, symmetric about
Even
origin
function.
is even function. So cosine
Yes.
function is even function. So if I like to have the Fourier sine function, that means we have to extend the function oddly. And if we have to get the sine cosine function, then we have to extend the function evenly, right? Now come to the here. That means in the other half, we like to extend it like f of x equal to f minus of minus fx for x belongs to this interval, this portion. I like to extend it oddly. Okay.
Yes, sir.
Okay. Then ultimately, what is your Fourier series? There will be no cosine
Yes, sir.
terms. So only
A not
Bn
A and
sine,
0, sir.
An will be 0. Only these
A
things
not
will
will be
be
0.
coming. Okay. Pn 2 by L 0 to L, only 0 to L. Why? Because it is even ultimately. This function is odd, sine is odd, product of two odd function
how
is
to
Even sir, even product of odd even.
Actually minus L to L chilo na. This is if this
And
function
sir, where is A naught? We will not write A naught.
A naught
N0
is
zero.
what is the definition? Fx is equal to A naught is equal to 0. You see, A naught is 1 by L minus L to L fx dx. And if your f is your odd function, then what will be this integration?
Zero.
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 No, sir.
Zero. That is why there is no A naught. So A naught and
Yes.
AN both all are 0. Only Bn. And Bn will be 2 by L. This is one step jump basically. Because the product of two odd function is even function. So we can, if your function is even, all of we know, minus A to A, fx
2
dx
0 to
jodi
L.
f.
2
So this
0
is
to
2
L.
into 0 to A,
0 to a
fx
fx
dx.
dx.
Fx
Yes,
dx.
sir.
So that thing is used here. Clear? Okay.
Yes, sir.
Now, on the other hand, if your function fx is defined in the 1/2 means 0 to L, and it is required to express fx in terms of cosine series, then what we have to do? We have to
Yes, sir.
extend the
Bn
function
zero. Sir. Bn zero.
evenly, right? Fx equal to f of
Yes, sir.
minus x. So this definition we have to apply. And as a result, what will be? Bn will be 0. So n and a naught, these will be the terms. And an will be like this, and a naught all of you know. Okay. So example, so these things basically all of you can do at your own, because this is nothing but your integration. It involves only integration. Half range Fourier sine series. So we have to look at whether it is sine series or cosine series. We have to find. If it is sine series, then what we have to extend?
So
We have to
oddly.
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 If it is
Combination of n.
cosine series, then evenly.
Yes,
Okay.
sir.
So
Evenly.
accordingly, the terms will be coming. Okay. Now applying your Fourier convergence theorem, then we can say that this thing. Okay. Example 4.2. You see, summation 1 by n square equal to pi square by 6, we have to show from the given series. Okay, I like to give some remark here. Okay, should I continue up to 10? Is there any problem?
Yes, sir. Do this
Yes,
sum.
sir. Other class, sir.
Other class, sir.
So another 2-3 minutes I like to take.
Okay, sir.
Okay, sir.
Then no problems.
Okay. Okay. Now you see here, fx domain of definition is what? Fx is what? Fx is x square. This is your fx. And domain of definition is minus 1 to 1. And we have to apply f of x plus 2 is equal to fx. Okay. Now you see that the function is continuous. So we can say that it is piecewise continuous, no problem. Continuous function is very good. And it is also differentiable. So it is also piecewise smooth. In fact, it is a smooth function. So it will be piecewise smooth. No problem. Okay. Now, so we can say that the Fourier series of f of x equal to x square will exist, and it is also convergent at all the points, because the function is having not a single point discontinuity inside the domain of definition, right? So regarding the fundamental theorem of Fourier series, Fourier convergence, there is no issue, because it will the series will converge for all points in the domain of definition. That is the point we have to know. And what is your a naught? You can find immediately, because x square is the function. A naught will be this thing, 2 by 3. So half a
Yes, sir.
naught
2 by
means
3,
1 by
sir.
3. 2 by
Yes,
3
sir.
it will be coming. So half a naught
Yes, sir.
means 1 by 3. And an cos nx, bn will be 0. An will be minus 1 to the power n. N will be minus 1 to the power n, 4 by n square pi square. This will be coming n. So n cos n pi x by L is 1. You know L is 1. So ultimately it is n pi x by 1 means n pi x. So this is fine. So this part is fine. Next part is that we have to give the proof that it is summation 1 by n square equal to pi square by 6. Now 1 by n square is coming. So this thing cos n pi x equal to 0. Sorry, it has to be 1. For what
Yes,
values of n it will
0,
be?
sir.
For
X0. X0.
x equal to 0. So if
Yes, sir.
we put x equal to 0, then also the series has to converge because it is
Yes.
convergent for all the values of x, right? Okay, so left hand side will
Yes.
be 0. Right hand side will be 1 by 3 plus summation 1 by this 1 minus 1 to the power n will be coming 4 by n square pi square. This is also coming. Cos 0 means, oh no, you cannot put n equal to x equal to 0. You have to
No,
put
sir.
x equal to in
Pi.
such a way that x equal to pi no, x equal to 1
Pi square
cos
by
n
4.
pi.
So x equal to 1 by n or something.
No, x equal to 1 hole ki hobe cos n pi. What is cos n pi? Minus 1 to the power n.
Yes, sir.
So
Yes, sir.
minus 1 to the power n is will be
No.
coming minus 1 to the power twice n.
Yes, sir. That
Yes.
will be 1.
1.
So x will be 1. So left hand side will be 1 square means 1. Right hand side 1 by 3 plus summation n greater equal to 1 minus 1 to the power twice n. It will be
1. 1.
4n
That one.
Yes.
4 sorry 4
Yes, sir.
by
Coming pi square by 6, sir.
yes n
Yes,
square
sir.
pi
2 by
square.
3. Yes, sir.
Now you understand this is easy how the proof is coming.
Yes, sir.
I said yes, I said initially that after today's class you are in a position to give the proof, and it has been given. It was given. The proof was given by Ramanujan. Okay, so this much for today.